In this lesson, in Unit 2, Lesson 11, we're going to talk about logarithmic functions. And we're going to be looking at those patterns again before we get into just an example with real-world application. Some quick checklists. If we have a logarithm, we want to know this basic shape, right? It's kind of like exponential, but it's kind of turned outside. X-intercept at 1, 0. We have our vertical asymptote, which is x equals 0. If b is greater than 1, so what we see there, then we kind of see what's happening to the function. It's increasing. Okay, see how it's increasing right there? Now, if that would be between 0 and 1, then it would be decreasing. Then what we have is the graph contains the points 1, 0, which we talked about. And then remember, whatever that b is, that's that point. So if it's log base 5 of x, remember what happens. Log base 5 of x, we change that into an exponential function. It's 5 to the y equals x. And there's that 5 right there. That would be 5, 1. And then if I took the fraction of it, it would be 1/5 down here. And the last thing is we can see that it's smooth, right? It's continuous. There's no breaks in the graphs, right, as it goes from one to the other. Yes, it has an asymptote, so it wouldn't have a domain of negative infinity to infinity, but again, no breaks within this part of the graph. So if we look at these different functions and we want to talk about the domain, we know that this domain really lies within where those parentheses are. So when it's just x, we know it goes from here to here, and if you think about those values, they have to be greater than 0. So these values have to be greater than 0. We know this shifts it to the left 5 units. So what that really means, if you think about it again, it has to be greater than 0. So that would be x is greater than -5. So our asymptote, or I'm sorry, our domain would be -5 to infinity. So everything above that. This one gets a little bit more complicated in the sense that this also has to be greater than 0. And so for this to be greater than 0, two things have to happen. The numerator and the denominator have to be greater or positive, or the numerator and denominator both have to be negative over negative. So if they're both positive, then we have to set the numerator greater than 0. And then we also have to set the denominator greater than 0. So what we get is negative x is greater than -1, x is less than 1. Or over here, we get x is greater than -1. To be negative in both the numerator and the denominator, it would have to be 1 minus x is less than 0, because it needs to be negative, or it needs to be 1 plus x is less than 0. Again, that's because this number right here has to be positive, right? By definition, we saw that the domain has to be on the right side. So now when I go to solve it, it's -x is less than -1, x is greater than 1, or over here, x is less than -1. And so now when we go to look at this and we look at our options, we can either have this and this happen. So x is less than 1 and x is greater than -1, which is plausible, right? Because if 1's here, it's going this way. If -1's here, it goes this way. So we have this overlap. Now, when we look down here, and again, if the numerator needs to be greater than 1 and the denominator needs to be less than -1, 1's going this way, -1's going this way, there's no overlap. So x here and x here can't exist in the same realm, so this doesn't exist. So when we're talking about our domain for this, it has to be an x where it is greater than -1 or less than 1. So -1 to 1. Now, when we look at absolute value right here, again, absolute value of x minus 2 has to be greater than 0. Well, absolute value, again, two different equations. X minus 2 is greater than 0, and x minus 2 is less than 0. Now, normally, this would be that number, and then we negate this, but positive 0, negative 0 are the same thing. So x is greater than 2, and x is less than 2. So what we have here is we have negative infinity to 2 union 2 comma infinity for the domain. For example number 2, it just wants us to match the equations with the variables. So what I'm asking you to do is to take 2 seconds, pause the video, or more than 2 seconds, pause the video and match the equation with the given graph of A, B, and C. Okay, for f, function f, notice there's no transformations whatsoever. So we're looking for our graph that's kind of your stereotypical logarithmic graph, just that goes like this. So which one matches that? That's C. So we're going to put C right here. Now, when we look at G, we see a negative x. Now again, normally what we've talked about is the reflection happening at x, but what's really happening is it's reflecting over the y because the x values swing to the other side. So we want this graph and we want it to swing over to the other side of y. So think about what that would look like, and that letter is going to be A. Over here, again, this is affecting the y values. The y values go from positive to negative. So again, think about that stereotypical graph right here. And now the y values change. So when the y values change, it flips this way. So it's going to reflect over the x-axis, which would be B. And then D, this one's a little bit trickier. I'm sorry, K, function K, which will be D. Think about it this way, log base 2 of negative 1. That's the same as 1/2 to the negative x. So a couple things happen. So if I set this equal to y, I'm going to have 2 to the negative first raised to the y power equals negative x. So not only do we have a reflection here, we're going to have a reflection here. So again, double reflection. Once over the x, once over the y, we end up having D for this one. Now, just like we talked about up here with this part reflecting over the y, so this reflects over the y, this part reflects over the x. So that's what this means real quick. So that's that negative exponent right there. So if it reflects over the x-axis, it would have the same graph as B. This is just kind of having us look at a parent graph of a logarithm to some translations and thinking of the rule. Now, they filled in the x values. I really, really highly recommend that you don't do it that way. If you do it like this and change it to the exponent and then fill in your y values first, so really filling in these values and then the x, it's going to work a lot easier. But if we put x in 1, what does y have to be? It has to be 0. If we put in 2 for the x, y would have to be 1. If I put in 4 for the x, the y would have to be 2. And if I put in 8 for the x, y would have to be 3. And we've seen this graph numerous times. It's here, it's here, and it's here. Oh, I forgot the 4. 4, 2. And it swoops like this. We have that graph. What's asking us to do then is to think about what's happening here. What's the translation? Well, this affects the y values. So what happens is it's going to reflect over the x. So if it reflects over the x, you know, this one's going to stay the same. This one's going to swing down here. Again, it's changing the y values. That's what's happening. So this coordinate point right here, let's do it in red. This coordinate point right here is 4, 2, and this one is 8, 3. That blue point will be 4, -2, and this will be 8, -3. So it swoops, reflects over the x, and it goes down like that. Notice axis of symmetry stays the same. So when we go to fill in that t-chart, it's going to be 0, 2, 4, 8. The x's didn't change, but the y values do. So what would the rule be? Well, if the function is xy for every point in f, then g of x would be reflecting every y value, so it would be x, -y. It asks us to kind of analyze the two graphs. So if I look at f of x, our domain is 0 to infinity. The range is -∞ to infinity. It is increasing and concave down. X-intercepts 1, 0, and we have a vertical asymptote of x equals 0. Go ahead, pause the video for a minute, and do the exact same thing for g of x. Find all that information. Okay, you can kind of look at that information for g of x. Pause the video, make sure that you have that correct. 4 is just taking a deeper look at those end behaviors based on the manipulations of the graphs. So, what I highly suggest that when you guys do something like this, and I'm going to do B, A is a little bit simpler, but when we do B, and I kind of rearrange it like this, okay, we can see a couple of things. This 2 means it is, so I'm going to backtrack in just a second. What we want to do is, because it's a quantity, I'm taking out the negative, so it's x minus 2. So if we look at this as x minus 2, that minus 2 means it has an opposite kind of direction affecting horizontally, so this is going to go to the right. And this negative out in front does a reflection. And the reflection is going to happen over the y-axis because it's going to affect the x. So if an x is over here as a positive, and it becomes a negative, it gets sent over here, so it reflects over that y. So make a sketch. Think about what's happening. So if we know that that typical graph looks like this, we know that there's a reflection over the y, and it's moving right 2 units. So now that graph is getting moved, and it's reflected like this. So now that green graph is really what we're looking at. So again, I encourage you to actually draw it out to kind of understand the behavior. So it's asking for a couple of things. It's asking for the vertical asymptotes. So the vertical asymptotes, actually there's only one vertical asymptote. It got shifted to the right. So it's going to be x equals 2. And then it's talking about the end behavior, and that talks about the limit, right? So if we look at the end behavior, 2 things are happening. It's going to negative infinity, so let's start there. It's going to negative infinity. And what's happening to the y values? Well, those y values are increasing. So as x goes to negative infinity, the y will go to positive infinity. Now, it can't go to positive infinity for the x. It goes all the way up to 2 and from the left-hand side. And so what's happening as it approaches the asymptote? Well, the y values go down forever, so it's negative infinity. Pause the video, quickly make a sketch of all 3, write down the vertical asymptotes and the end behaviors in limit notation. So for letter A, we can see, hopefully we can see that -1 within the parentheses is going to make the shift of the graph go to the left. Sorry, that shouldn't have been to the left. It should go to the right. I apologize. Let's fix that up. So it goes to the right. On my vertical asymptote, just didn't have the graph correct. So as it shifts to the right, the vertical asymptote also moves to the right. So it's at x equals 1. You can look at the end behavior, it's going open-ended to positive infinity. And as it's going to infinity, it's going up, so to infinity. The asymptote being here, it means it cuts off how far it can go. So as it's getting closer to 1 from the right side, it's going down, which is negative infinity. I'm going to jump to D. D has a shift down 3 units. So the vertical asymptote doesn't move, just the graph shifts. So it's at x equals 0. And really that end behavior doesn't change as well. So as it approaches 0 from the right, it's still going down to negative infinity. As it's going to positive infinity, it is also increasing, so it's going to infinity. C has a lot going on. The 2 makes it move up. The 4 makes it shift to the left. And then this negative on the outside of the logarithm makes it reflect over the x-axis. So this graph, again, has a lot going up. It shifted up, left, and reflected, okay? So the vertical asymptote now moved to -4, x equals -4. And you can kind of see that end behavior. As x approaches infinity, it's going down, okay? I know it doesn't look like it for my graph too much, but it is going down. So it's negative infinity, and it's approaching now -4 from the positive side, the right side, and it's going up, which is infinity. For example, number 5, I want you to go ahead and just plot these points, and it's just asking you to define whether it's increasing, decreasing, concave up, concave down, okay? And then the domain. So go ahead, take a minute, pause the video, do these problems. Okay, so hopefully yours looks very similar to mine. I plotted the points, and you can see it's increasing, right, as it's going left to right. It kind of has that frown, so it's concave down. And I said from +1, that it's going from +1 to infinity, because at 1.1 is just past that. You can kind of see how it's kind of going down pretty quick. So I would say that's probably where that asymptote is. B, it's decreasing left to right. It's concave up because you have that smile part going on. And again, same sort of reason. I said -2 because -1.9, should probably be closer over here, is just slightly on that side. You can kind of see how it's tapering off. So that domain is -2 to infinity. All right, number 6 shows the application, basically with an investment. So a principal P invested at 6.25% is compounded continuously and increases to an amount K times the original principal after 2 years, where T equals ln(k) over 0.0625. So you can see the logarithm or natural log with, log base E. And here's the thing I want us to think about. If I rearrange this, okay, what we have is I would multiply by 0.0625. So 0.0625t equals ln of k. ln is log base E, so it would be E to this over here equals k. That's what we're really looking at, right? And then that should look familiar, because usually then what happens is we have our starting principal right here, whatever we kind of enter in. So if I start plugging these in, I get 1 is 0, 2 is 11.1, 4 is 22.2, 6 is 28.7, 8 is 33.3, and 10 is 36.8. Again, all I would do is take k And I would plug it in here because then it finds you t. But again, this is kind of what we're kind of looking at. So using a graphing utility to graph the function, well, we could also kind of use our points up here, 10, 38, and it's just a real rough sketch, but you know, if we want to go out, you want to put that on your calculator. You could also put on Desmos. This will kind of help you get that sketch that's happening. And then this one says, suppose you have $1,000 to invest. Your function, use your function for the amount in the account at any time t would be this. You can kind of see that's what we had up here, right? Very similar to that expression where 1,000 is that principal that you're putting in. So we're verifying it and we're saying, okay, it should take us, oh, I should actually go back to here. It asks us to figure out when it doubles. Well, it's going to double, okay, our investment doubles at about 11.1 years. So if that's really what I'm trying to see, is I would take 11.1 and I would put it into my calculator, into this formula, so 0.0625 times 1.1, and I would see approximately what I get. So go ahead and do that. And you get, hopefully, about $2,001.21. And I think it's a pretty good estimate, right, of doubling our money. It's pretty appropriate for what we're trying to get. So I think it's a pretty good estimate.